So our next chapter is chapter number 7, impulse and momentum. What is impulse? Impulse is uh, a force acting on a body or an object on a certain amount of time. So if, let's say, if there's an object and if we apply a force for a certain amount of time, so combination of force and time, we call it impulse. How about momentum? What is momentum? So momentum is a resistance to stop. For example, if a very small object moving with a large speed, very large speed, it is hard to stop. Similarly, if you have a very heavy object moving with even very slow speed, it is very hard to stop. So momentum is reluctant to stop. So it's a combination of mass and velocity. Combination of mass and velocity, we call it momentum. Impulse is a combination of force and time. Force acting on an object in a certain amount of time. And also momentum is a combination of mass and a velocity. In this example, we see in a very short amount of time, we apply a force. It's like average force is like this. So when we hit the ball, the time is very small time, and very large force acting on a very small period of time. So the definition of impulse. The impulse for force is the product of average force and the time interval. F times time is delta t, it's a very small time or time interval, time change. So we use J for impulse. So we use J for impulse, force, average force, and the time interval. So the units of impulse is units of force, which is Newton, and units of time, which is seconds. So unit of impulse is unit of force times units of time. So Newton second. So the definition of linear momentum. I will tell you why it's linear, because after I derive this equation, so we use P for momentum, which is equal to mass times. So velocity is a vector, so which means mass is a scalar, no direction. Velocity has a direction, therefore momentum has a direction. Therefore, we had to consider a certain direction. So linear along a certain direction. So therefore, we call it linear momentum. So momentum is equal to mass times velocity, and unit of momentum is unit of mass, which is kilogram, and unit of velocity is meter per second. So unit of momentum is kilogram meter per second, kgms, -1, or kilograms meters per second. Beginning of this lecture, we derive a equation for impulse. We use J for impulse, which is force, average force, times time interval. So now I'm going to combine this force. We know how to derive the force in terms of using Newton's second law, and instead of force I can write this is net force, Newton's law, mass times acceleration, and net force is mass times, instead of acceleration I can write v final minus v naught divided by time. So time interval I can write delta t. So if I rearrange this equation, F times delta t is equal to mass times v final minus v naught. So we know F delta t is impulse. So again, instead of the impulse, we know F delta t, and we have another equation for F delta t, which is mv final, mass times final velocity minus mass times initial velocity. So impulse, now we have two equations, F times delta t, which is equal to mv final minus mv naught. So we have two equations for impulse, F delta t and also mass times v final minus mass times v initial. So momentum is mass times velocity. So m times v final is final momentum. mv is momentum, v naught means initial, therefore initial momentum. So impulse F delta t is change of momentum. When net force act on an object, the impulse, which is impulse, is equal to change in momentum of the object. Momentum is mv final minus mv initial, change of momentum, which is equal to impulse. Impulse and momentum, we're going to take two examples to see how we can apply this equation, impulse and momentum, final and initial, and how this impulse change depending on incoming and outgoing velocity. So in the first example, we see a raindrop coming down and hits a roof of a car. So when it hits, it flattens and there is no bounce back. So therefore its final velocity of the raindrop is 0. So if we use this equation, so this term is mass times mass of the raindrop times velocity of the raindrop after it bounces back. Since it's not bouncing back, this term is 0. So the question is, what is the average force, which is force? I can write force equals, I can divide both sides by delta t. So I have m over delta t times v naught, initial velocity. M over delta t is mass per time. It is given. So if I use, which is 6 kilograms per second, and v naught is minus 15 meters per second. Okay, so plus 0.9 kilograms meters per second square, which is Newton. So, okay, in this example, instead of rain droplet, let's consider a hailstone. So falls on the roof. Let's assume the same speed, negative 50 meters per second. And let's assume it bounces back. Let's assume it bounces back with the same speed. I'll put 15 plus meters per second because it's in opposite direction. So if you calculate the force, now the final velocity no longer 0. Now you have F m over delta t. Now you have v final minus v initial. So m over delta t is 0.9 or 6. V final is 50 minus V initial is negative 50. So now your force is double. So the previous example, when the raindrop hit, your force was 0.9 Newton. So now your force is 1.8 Newton. If the hail stone come bounce back with the same incoming speed. So I use 15, same speed for simplicity, but it bounced back. Therefore, it make a larger force. Right? This is the reason when hailstone hits a roof, it make more damage because it creates a larger force compared to a raindrop. In the previous chapter, we talk about work energy theorem or conservation of energy. The final energy of a system is equal to initial energy. So energy consists with kinetic energy, half mv final square, motion of an object, and also potential energy, mg final, position of an object relative to the surface of the earth. And initial energy, kinetic part is half mv initial square plus mg h naught initial height. So in this chapter, our next question is, can we write a similar equation for combining impulse momentum? And next few slides, I'm going to show you how to get a relationship between impulse and momentum, which is somewhat similar to this equation we use for conservation of energy. Okay, I'm going to show you how to derive conservation of linear momentum. Before we talk about the equation, let's talk about internal forces and external forces. These two are very similar to what we talked about in the previous section, conservative forces and non-conservative forces. So let me give you an example. Let me draw a flat surface and two objects. Let's say mass 2 and it has a velocity 2, and I have another object coming towards the second object with the velocity v1 and it has a mass v1 m1. So if these two objects come and hit or collide at one location, during this travel, if there is any wind, any direction, it can cause to change the speed because of wind. Or let's say we tap on this ball with a small force, then we apply these forces we call external forces, because these are external to these two balls traveling on a flat surface we can consider as one system. Anything external, it can be wind, it can be resistance, it can be force you apply onto one of these objects. Those for every other thing external to this system, we call it external force. So these external forces is by nature it's there. So when there's a collision between two objects happen, we have internal forces and also external forces. So when we derive, we can assume external forces. We can disregard the external forces and we just consider the internal forces and derive a equation. Let me show you in the next slide. Okay, this is the equation we learned for impulse. Average force times time equals final momentum minus initial momentum. So if I write, these are two objects, object 1 and object 2. So after the collision, object 2 apply a force on object 1, and also object 1 apply a force on object 2. So I'm going to write this equation 2 times for object 1 and object 2. Okay, so external forces on object 1 plus force on object 1 by object 2 times delta t, mass of object 1, velocity of object 1, final velocity of object 1, minus mass of object 1, initial velocity of object 1. Similarly, I can write a similar equation. External forces on object 2, force on object 2 by object 1, and mass of object 2, final velocity of object 2, mass of object 2, initial velocity of object 2. So I'm going to rearrange this equation. I'm going to add this equation to the second equation. So when I add these two equations, I have W1 plus W2 and force on 1 by 2, force plus force on 2 by 1. So these two forces are equal in magnitude because it's the Newton's third law. A on B is equal to B on A. So therefore these two forces cancel because magnitude wise same, direction wise opposite. So therefore we can cancel these two forces. And mass 1 times V final 1, mass 2 V final 2. So mass times V is momentum. So this is final momentum. This is mass of object 1 times initial velocity of object 1, mass of object 2 times initial velocity of object 2. So this is the initial momentum. So now we have W1 plus W2. These are external forces on object 1 and object 2 equals final momentum minus initial momentum. Okay, so W1 plus W2 is sum of average external forces times delta t, which is equal to final momentum minus initial momentum. If the sum of the external forces are 0, if we assume this side is 0, which is equal to P final minus P initial, if I rearrange this, final momentum equals equal to initial momentum. So final momentum is M1 V1 final, M2 V2 final, which is equal to initial momentum M1 V1's initial, M2 V2 initial. So principle of conservation momentum. Again, it's linear because momentum is a direction, has a direction, because velocities, those are has particular direction. When you write these equations, you have to consider a particular direction. So the principle of conservation momentum is the total linear momentum of an isolated system is isolated system, because we assume there are no external forces, is constant or conserved. An isolated system is one of which the sum of average external forces acting on the system is 0. Remember, when we derive this equation, we assume there are no external forces. So let's do a couple of examples using this conservation of momentum so that you can understand how this equation works. Okay, here's another example. The question is the total momentum conserved. The momentum of conservation says momentum of an isolated system is conserved. Isolated system. So in this example, we consider two ball collision. That's a isolated system. And in addition, this is an isolated system. In addition, it says collision on a billiard table. that is friction free, which means there is no external forces. So therefore we know we can use the conservation of momentum, which says the final momentum is same as the initial momentum of the system. So which means the total momentum of the two-pole system is conserved, and the two-pole system, the momentum before and after the collision are same. However, the part B, answer part A for system that contains only one of the two collisions. So if we have only one ball, which means it's not a complete system, so therefore we cannot apply conservation of momentum, and we have only force on 1 by 2 and external forces on object 1. So when we derive this equation, remember we use force on 2 by 1, and we cancel those forces 1 by 2 and 2 by 1. But if you consider just 1, it is not a complete system. Therefore, we cannot use conservation of momentum. Okay, here's another example. It says starting from rest, two stakers push off against each other. So if starting from rest, so if this is 2, V2 initial is 0 because it is starting from rest. Even this person, let's say 1 initial, I put 0 is initial, is rest, which means 0. So 1 is 55 kilograms and 1 is 88 kilogram man. So M mass of the man is, I put 2, 88 kilogram. Mass of woman, M1 equals 54. So the woman moves away with the speed. Find the recoil velocity of the man. So friction is negligible. So which means external forces are 0. So therefore we can use the conservation of momentum equation. So final momentum is equal to initial momentum. So of the system. System means man and the woman. So momentum, final momentum of the man is mass of the man, which is 88, and velocity of the man, we don't know, V final 2 plus mass of the woman, which is 54, and velocity of the woman, she is moving with plus 2.5 meters per second, which is equal to initial mass times velocity. So initial velocity of the man is 0, therefore momentum is 0, and mass of the woman is 54 and her velocity also 0. So initial momentum of both man and women is 0. So we have only this equation, 88 V final 2 is equal to negative 54 times 2.5. So now you can solve V final 2, which is equal to negative 54 times 2.5 divided by 88. We get a negative sign because women moves this way with 0.2.5 and most goes on the opposite direction. So opposite direction means we have a negative sign. And when you solve this equation, you can get the man speed 1.5 meters per second. 1.5 meters per second. It's a negative because it's on the opposite side. Women goes speed is 2.5. Notice she has a higher speed compared to the man. The reason is man is heavier because he is 88 pounds kilograms, and women is 54 kilograms. So lighter the weight, lighter the mass, higher the velocity. Higher the mass, lighter the velocity. Collision in one dimension. So elastic collision and inelastic collision. You will see these two words, elastic and inelastic, in your lab number 7 I assigned to you yesterday. This is the reason I asked you to wait till today until I cover this section to complete your lab. So inelastic collision, here's an example. In figure A, you see a ball comes and hit a surface and it bounced back, so to the same level. So you can see it's elastic, it comes and goes. So one in which the definition is the total kinetic energy of the system after the collision is equal to the total kinetic energy before the collision. So the total kinetic energy of the system before and after are equal. Okay, so what is the kinetic energy? Kinetic energy is equal to half mass velocity square. So if the velocity of this object coming back and going up are equal, their kinetic energies are equal. So here it has a velocity, and when it going bounce back, it has a less speed or velocity because it doesn't go all the way up to its initial position. So it has a less energy. So which means the total kinetic energy is not conserved or it's equal. So therefore we call it inelastic. So inelastic collision is the total kinetic energy of the system after the collision is not equal to the kinetic energy after the collision. There's another item to that. Objects stick together after the collision. The collision is said to be completely inelastic. So in your lab, there are 2 or 3 sections. One is face-to-face collision and then bounce back. It's like elastic. Another one, there's a collision, but it is inelastic. Okay, and third one, they hit each other or collide each other. They collide each other, but after the collision, they stick together and travel as one unit. Then again, after the collision, if the objects stick together after the collision is completely inelastic. So in this case also inelastic. So make sure you understand the difference between elastic and inelastic when you work on your homework. Initial speed. Okay, I'm going to show you 2 examples there. In this topic, we're going to talk about 2 dimensions before you go to 2-dimension collisions. Let's consider linear collision. So initially, this is before, this is after the collision. Okay, there are 2 cases. Before the collision, the mass 2, the same mass because similar balls, so same mass 1 kilogram each. This is at rest. Therefore, V2, the second mass, initial speed is 0, and let's say V1 has a velocity of 2 meters per second. After the collision, V2 has a speed, let's say 1 meters per second. Question is, what is the speed of the first ball after the collision? So we can use, if there are no external forces or friction, we can write conservation of momentum, so which is mass of ball 1, which is 1, and velocity of ball 2, ball 1 is 2, plus mass of ball 1 plus times velocity is 0, therefore it becomes 0, which is equal to mass of ball 1, which is 1, and the speed we don't know, v1 final, plus mass of the ball 1 times speed 1, because it's in the same direction. So 1 times 2 is 1, which is v1 final plus, I'm sorry, this is 2. So v1 final is 1 meters per second. So this speed also 1 meters per second, because initially it has 2 meters per second, and after the collision this become 1 meter, and then this become 1 meter, because initial speed basically split between these two, because the second one also has a mass. Now let's assume, it's the same case, it's coming along the same linear path, but after the collision the 2 goes to an angle to this linear direction, like 30 degrees to an angle. Now how are we going to calculate v1 final? Because remember the initial equation, mass of v1, velocity of 1 initial, plus mass of 2, initial velocity of 2 after the collision, which is equal to mass of 1 v initial after the collision, plus mass of 2, velocity of this is final in 1, this is 2 final. So velocities has a direction. So here it's a linear direction, but when you have a special case, or two-dimensional case, we need to make sure we take the velocity along x direction and y direction. Okay, so if I write along x direction, I can write same equations. Mass of y1 times velocity of v1, which is 2. Mass of 2 is 1, but velocity is 0. After the collision, mass of 1 times velocity v final 1 plus mass of 2, and now velocity 1 cosine 30. Okay, so now again we can calculate v1 final after the collision. Okay, so make sure when you use two-dimensional motion, you have to use the velocity along that particular direction. So